over 2, and that might happen for a different index. Good. Then take the maximum of both indices beyond which both of these things are true. That's the basic idea. So, very nice argument. We're going to fix epsilon bigger than 0. We're going to start with that. And now, the Cauchy part, so xn Cauchy implies what? Well, there exists a, let's say, big N, such that if I and j are bigger than big N, then this means that the distance between x, what? I and x j is what? Less than epsilon over 2. Everybody happy with that? So we've just taken care of showing that past some point in the sequence, all the terms are close to each other, right? Okay. What else? What else can we say? xn k converges to x. I agree. Okay, so let's say this converges to x implies. Yeah, let's call this n1, let's call this n2, such that, help. Sorry about that. Just coughed. Okay, so there is big N2 such that anytime you have something bigger than, little n bigger than big N2 implies, okay, we have to be a little careful here, but yeah, I mean, we're just saying past some point in the sequence, the subsequence converges. Now, would you agree I could write this in terms of k, or I could write it in terms of n? And just for ease, I'm going to write in terms of n. So such that whenever n sub k is bigger than n2, this implies the distance from x sub nk to x is less than epsilon over 2. Yeah? Okay, help me here a little bit. So what is it I would like to say? We have to be maybe just a little careful here. So I want to eventually show that past some point in the sequence, in the big sequence, I can get within epsilon of x. So what point should that be? Okay, you'd like to take the max of n1 and n2? Is that right? Okay, let's see if that works. If it doesn't, we'll have to modify a few things, but this is certainly the first thing to try. Let's let big N be the max of n1 and n2. Okay. And now the goal is to show, so if n is bigger than big N, then what can we conclude? Well, first we're going to bound the distance from xn to x by the triangle inequality, which would be what? Oh, well, now we have to sort of specify an intermediate point to compare to, right? Maybe that's an issue, something we have to deal with first. Right, so I'm gonna finish writing this out, but this is sort of where we're heading. So I might have to insert something here. But the point is, xn, if it's bigger than big N, the claim is that there's some other point, x sub what? nk, that I want to compare to. And the only problem is, this is a huge problem, is that I actually haven't said what x sub n sub k is. right? So I probably want to insert here before this line a line in between, right? So the line in between should say what? Pick an n sub k bigger than n. And do we know that one exists? Yeah, because it's a sequence, and of course, a subsequence, it has to eventually, there are infinitely many terms and only finitely many things before nk. So in fact, I'm gonna just do that here. This is less than or equal to this plus this in fact, for any n sub k bigger than n, this should be true, right? For any n sub k bigger than n. We should actually fix one so that we can finish this argument here. So I'm just going to fix one. I don't care. And now this is less than what? Epsilon over 2. This is less than what? Epsilon over 2 by construction, which is epsilon. And so what have we shown? We've shown that no matter what epsilon you give me, this distance is less than epsilon as long as, and I found an n for which that works. Okay. So given epsilon greater than 0, we found an n that works. That shows convergence of xn to x. Okay, everybody happy with that? So we've used the Cauchy not the criterion, the Cauchy definition here in a very essential way. So what does this mean? Oh, this means that x is complete, yeah. And this is true for any sequence. So I'll just write a sentence that xn was arbitrary. Big X is complete. That's the end of the proof, actually. Okay, very nice. So this actually now shows that 0, 1 is a complete metric space, right? So corollary, 0, 1 is complete. Oh, not only that, if you want to look at some compact set in a larger space, right? Isn't the the K cell complete? K cells are complete. What K cells? I mean the ones in Rn. Lots of things now we know are complete. Okay. So does this mean that, can we show, do you think that Rn is complete? It's not compact. Do you think Euclidean space is complete? How many people say yes? How many people say no? Objection?
Oh, no, it's just a guess.
It's just a guess, and I applaud you for being bold and taking a stand against the opinions of others. Do you think it's good though? It's good, but it's not the right answer. Why is Rn complete? Can you see why? We've just shown that compact spaces are complete. Even though Rn is not compact, can you show that it's complete? Can you show that every Cauchy sequence converges? Jenny?
Well, you could show that every Cauchy sequence is bounded, and then from there you can just look at that portion of Rn and show that then since it's contained within a compact space.
Excellent. Excellent. Good. So that's in fact our strategy. I just noted here in my notes here, I wanted to mention one more thing. Another example of a complete spaces. If you take a closed subset of a compact set, it must be complete, right? Because